The accretion and formation of Earth, approximately 4.6 billion years ago. Approximately 4.6 billion years ago, in a remote region of the Milky Way galaxy, a grand event unfolded that led to the birth of the solar system and our planet Earth. Everything began with a solar nebula, a colossal cloud of gas and dust, primarily composed of hydrogen and helium, along with trace amounts of heavier elements forged by previous generations of stars. This nebula spanned hundreds of light years across, rotating slowly in the cold void of space. A shockwave from a nearby supernova explosion, or the pressure wave from a young star, triggered its gravitational collapse. As the central density increased, so did the temperature and pressure, eventually giving rise to the protosun at its core. The remaining material surrounding the young sun flattened into a vast protoplanetary disk, where the process of planet formation began. Within this swirling protoplanetary disk, microscopic dust particles just a few micrometers in size started colliding and sticking together through electrostatic forces and van der Waals attractions. This marked the beginning of the accretion process. Initially, these dust grains formed small chondrules, then gradually grew into centimeter-sized objects, then meter-sized bodies, and eventually into planetesimals several kilometers across. Gravity now played the dominant role. Larger objects exerted stronger gravitational pull, sweeping up material along their orbital paths. This phase occurred remarkably quickly, within the first few million years. Computer simulations suggest that within just 10 to 20 million years, hundreds of planetesimals had formed. These continued to collide and merge, creating protoplanets. Our primordial Earth was one of the fortunate protoplanets that survived this intense period of cosmic collisions. Once the young Earth reached a size close to its current diameter, the immense energy from continuous impacts, combined with the heat generated by the radioactive decay of isotopes such as uranium, thorium, and potassium, caused the entire planet to melt completely. This was the Hadean Eon, roughly 4.6 to 4.0 billion years ago, named after Hades, the Greek god of the underworld, because Earth at that time resembled a gigantic ball of molten magma glowing red-hot. Surface temperatures reached thousands of degrees Celsius. The entire planet was a vast magma ocean hundreds of kilometers deep. There was no solid crust, no liquid water oceans, and the early atmosphere consisted mainly of volatile gases released from the magma, including water vapor, carbon dioxide, nitrogen, and large amounts of hydrogen. In this chaotic environment, Earth was continuously bombarded by asteroids and leftover planetesimals. Massive impacts carved enormous craters and repeatedly vaporized any temporary crust that managed to form. Some scientists believe that during this period, Earth experienced at least one global melting event, powerful enough to liquefy nearly the entire planet. Despite the extreme conditions, the Hadean Eon was also crucial for Earth's differentiation. Heavy elements like iron and nickel sank to the center, forming the liquid outer core and solid inner core, while lighter elements rose to create the mantle and the precursor to the crust. This process released additional heat and helped generate Earth's early magnetic field, which would later protect the planet from solar wind. One of the most dramatic and important events in Earth's formation history was the giant impact with Theia, a Mars-sized protoplanet, approximately 0.5 to 0.6 times the mass of Earth. According to the giant impact hypothesis, around 4.5 to 4.4 billion years ago, Theia collided with the early Earth at a glancing angle and extremely high speed. The collision was not head-on but oblique, ejecting a massive amount of material from both planets' mantles into space. Millions of cubic kilometers of molten rock and metal were blasted into orbit, forming a colossal debris ring around Earth. Over the following months to years, gravity caused these fragments to collide and accrete, gradually coalescing to form the Moon. The birth of the Moon dramatically altered Earth's destiny. In its early stages, the Moon orbited much closer to Earth, only about 20,000 to 30,000 kilometers away, generating extremely powerful tides that caused massive magma waves across the planet's surface. The Moon's tidal forces also gradually slowed Earth's rotation from just a few hours per day to the current 24 hours. Furthermore, the Moon stabilized Earth's axial tilt, leading to more stable long-term climate conditions that would later support the emergence of life. Many scientists believe that without the Moon, Earth might have experienced wild axial wobbles, resulting in extreme climate fluctuations unsuitable for complex life. Following the Theia impact, Earth slowly began to cool. The first thin crust started to solidify, although it was frequently destroyed by ongoing impacts. By around 4.4 billion years ago, evidence from highly durable zircon crystals, the oldest known terrestrial minerals, indicates that liquid water already existed on the surface, at least in the form of shallow seas or lakes. This marked the transition from the chaotic Hadean Eon toward the Archean Eon. A secondary atmosphere began forming from volcanic outgassing and possibly from water-rich comets. Accretion continued, but at a much slower rate, signaling the end of the main formation phase. In summary, the formation of Earth was an epic cosmic saga spanning hundreds of millions of years, beginning from an invisible cloud of dust and gas and culminating in a molten rocky planet, followed by the creation of its constant companion, the Moon. Everything we see today, mountains, oceans, and life itself, originated from those violent collisions and the patient accumulation of matter within the solar nebula. Understanding this origin not only helps us appreciate our planet, but also raises profound questions about how rare Earth-like worlds may be in the vast universe. Word count, 1028.